In this video, I just want to show you a little application of average rate of change and instantaneous rate of change. And I also want to show you how you estimate the instantaneous rate of change from a table. So the context here is, let's see, it says the management of a new restaurant at the New Natick Mall did a study on the rate of change at which people enter their restaurant. The management needs to let their chefs know how much food to prepare at different times of the day. The restaurant opens at 12 noon, and the following table shows the amount of people in the restaurant T hours after its opening. So, just again, you might want to jot down, just so you remember, that we've got 0 hours, or this 0 in the table corresponds to 12 noon. So I'm just going to indicate that. All right, and then clearly everything from there kind of just makes sense, so we'll just remember that that's noon. So the first question says, determine the average rate of change of people entering the restaurant between 4 and 8. And anytime you get a question about an average rate of change, you're always just finding a simple slope. So at 4, it looks like there were 190 people, and at 8, there were 249. So I'm finding the slope between these 2 points. The points 4, 190, and 249, and 8, 249. So the change in y would be 249 minus 190 divided by the change in time, which is 8 minus 4. And we do that on the calculator and get 14.75. Okay, so that's 14.75. And pay attention to units, because the 249 minus 190, that was people, right? The units on that were people. And then 8 minus 4 were hours. So this is a rate. This is people per hour. Okay, in calculus, paying attention to units can often help you make sense of the problem. Then it says determine the rate of people entering the restaurant at 7 p.m. So pay attention to that word at, right? At 7 p.m., that means they're asking for an instantaneous rate of change, okay, at an instant. Now this can't actually be done because we don't have the function in front of us, so we can't use our analytical methods to get that instantaneous rate of change. So the best you can do, okay, the best you can do is estimate. So I'm going to say that the instantaneous rate of change at 7 p.m. Now this is going to be about equal to, meaning this is the best estimate we can do. So whenever you're asked to estimate the rate of change at a point and you're given a table, you always use the points surrounding it. And I'll show you why in a second. But for now, find the average rate of change of the points around it. So that's going to be 249 minus 234 divided by 8 minus 6. And that gives you 7.5 people per hour. So just briefly, the reason why you do that, the reason why you surround the points is because, for all we know, like if you get a function and it was going like this, if that's the point where you're trying to get the instantaneous rate of change, but all you don't have really the data, the info on the curve, you just have a point here, let's say, and a point here. If you find these two slopes, like let's say you found that slope, that's doing, I guess, an okay job of approximating the slope of this tangent line, but not too good. This one here also, it's okay, but it's not quite going in the same direction as the tangent line. But when you surround the points, when you surround the point and get the average rate of change between the 2 points surrounding it, you tend to at least produce a slope that's somewhat or plausibly parallel to the tangent line. So in any case, that's the best you can do. So always surround the point and find the average rate of change of the points around it. Okay, and C says, is your answer to part B accurate? Probably not, because, I mean, look at, we've got there's a 2-hour window that between 6 and 8. A lot of people can go enter a restaurant, and that's just too much time goes by to really get a good understanding of the true rate. So I would say no, not quite accurate, not likely accurate. Okay, too much time went by. In order for us to get a good approximation. So really what you would want, as we have done in previous lessons, what you really want is you want the amount of people at, let's say, 6:59 and 7:01, or 6:59 and 30 seconds and 7 o'clock and 30 seconds. If you knew the amount of people in the restaurant at those times, then you could get a much better estimate of the instantaneous rate of change, because not enough time passes for people to leave, and so your estimate for the rate would be much better. So where it says, how could your result become more precise? I would just say gather more frequent data. And I might just say, for example, at times, let's just say 6:59 and 7:01. So if you got data, down to the minute, you'd have a much better estimate of the instantaneous rate of change of people entering the restaurant. Okay, so that kind of takes care of estimating, and again, the big picture there was I wanted you to see that you use the points surrounding the point of interest to estimate the instantaneous rate of change. In the real world, very often, you gather data, and the math comes in the pure math comes in when you use a model to try to capture the data. So this would be like a model that would be used to describe the data, and it's easier actually to deal with the model because we can use the calculus we've learned. So part A says determine the average rate of change of people entering the restaurant between 4 and 8 using our function. So now we do what we've learned before. Again, it's just a slope, but it's just going to be f of 8 o'clock, minus f of 4 divided by 8 minus 4. Okay, and so f of 8 equals 248. F of 4 equals 188. And again, I'm just using the actual model, the model here, not the table. Divided by 4, so that's 15. So that's 15 people per minute. Hour. And so let's see, how does that compare? How does that compare to 1A? Because 1A, we also did that estimate from the table. It's actually pretty close, right? So our model's probably a pretty good one. If you were to plot all those points and then plot this graph, I bet you that graph goes through a lot of the points, which is what a model should do. So our answer is pretty close. Just jot that down. Pretty close. Determine the rate of change of people entering the restaurant at 7 p.m. using your function. So now we're not going to estimate the instantaneous rate of change. We're going to use our function and the analytical methods we learned to actually do it. So let's use the notation. This would be f prime of 7, and that equals the limit. And I'm going to use the x minus a definition. So I know I've taught you 2. So the limit as x goes to 7, f of x minus f of 7 divided by x minus 7. And in this particular case, that is the limit as x goes to 7 of negative 4x squared plus 63x. And f of 7 is equal to 245. divided by x minus 7. Now, one thing I should point out, and I should have pointed out when I did the other video, is that this numerator is guaranteed to factor, and it's also guaranteed to factor with a factor of x minus 7. So that is good news, because you don't have to really think a whole lot, in the sense that I know that x minus 7 is a factor here. Okay, so the other factor must be negative 4x, and let's just see if I can figure this out quickly. It must be 35, and it must be plus. Okay, divided by x minus 7. So you should notice what I did there. I didn't have to think too hard about the factoring, because I knew x minus 7 is going to be a factor, because it's rigged to work like that. Crossed off, and this equals, now we can substitute our 7 in. So this is the limit as x goes to 7 of negative 4x plus 35, and you plug in, you get negative 4 times 7 plus 35, so that's 35 minus 28, so you get 7 people per minute, per hour. I don't know why I keep saying minute. People per hour. Okay, and it probably asks us to compare that to what we got over in 1b, and if we look back, we see in 1b, pretty close, right? 7.5 was our estimate, and the model gives 7. So it's a pretty good model. Okay, and then lastly, the equation of the tangent line. We've done this before. So the point is 7 p.m. and the amount of people at 7 p.m., if we go back over here, is 245 people. Okay, so that's my point. And then the slope we just got the slope, that was 7. And so our tangent line would look like this. Y minus 245 equals slope x is slope 7, x minus 7.